Hi, my name is Oliver Taradash, and I'm doing this project on sound waves. And I decided to do this because I'm trying to learn guitar because all my roommates play, and I'm not good at all. But I thought this would be an interesting project, and it was doing the research with it. So what I'm doing is I'm trying to like when a guitar string vibrates, it forms a standing wave with nodes at each end. When the lowest vibration, it's called the fundamental frequency, and it depends on its length, the string's length in L, which is L, tension T, and the mass per unit length of μs. And the equation for this is, okay, and this is all my math, guitar string frequency. We have the frequency equals 1 over 2L square root of the T over the mu. So F equals the frequency in hertz. L is the length of the vibrating string. T is the tension in the string. And mu is the linear mass density in kilograms per meter. And my numbers are for the length, you have it in 0.65 meters, which is the length of the guitar from here to here would be 0.65 meters. The frequency is 440 hertz because I'm playing the A note, and the mu is 0.00015 kilograms per meter. This equation up here, I have all of my math up here. It represents that shorter strings make higher pitches, greater tension raises the pitch, and heavier strings make lower pitches. So we have the high E chord at the very bottom. It's the lightest string. And when I pluck it open, not holding on to anything, it's the heaviest, it's the lightest, highest pitching note. And I go to the low E on the top. Heaviest string, lowest note. And when I go E, B, G, D, A, E. And now these are the calculations for the tension needed to play the string at 440 hertz. So the rearranged equation is 2L frequency squared equals that. And that's the rearranged equation. And now it's going to be 2 times 0.65 times 440 equals 572 after the original equation of 2 times 0.65 times 440 squared times the 0.0015. It was 572 squared, which is 372,184. And now you times that number by the linear mass of 0.00015 kilograms per meter. And that's gonna give us 49.1 newtons. So now it says it takes about 49 newtons of tension to produce a 440 hertz note on this string. And now I'll be going into having the length of math. Now my first demonstration is going to be by showing you the full playing of one note at the full length of the string, and I'm going to be playing the A note, which is 440 hertz, and I'm just going to play it once, and I'm going to take note of the sound that it makes. I'll do it one more time. And now I'm going to go on the 12th fret, and I'm going to show you the difference in the notes. So these are all frets here. This is the 12th fret. Push down the 12th fret, and I play the same note. You hear the difference? This is the open. And now 12th fret. And when I press down on the 12th fret, the vibrating length is half as long. And according to that equation that I showed you, having L, like halving L doubles the frequency. That means that one note is 1 octave higher. So now that A note that I just played now turns into, from 440 hertz, doubles, now it's 880 hertz. And I would be able to show you that if I had a tuner app, but I don't. But that's just my second demonstration with the guitar. Is I'm going to be showing you changing of tension. And these are tuning pegs. They each correspond to one of the notes on the guitar. So when I tighten the tuning peg, the tension T as a variable using increases and the pitch rises. The frequency only increases with the square root of tension. So even a small change makes the pitch go up slightly. So now I'm going to play the A note. And now I'm going to tune it up a little tighter. You might not be able to notice it on the video, but it is going to get slightly higher while I tune it. Keeping on increasing it, getting a little higher, And now when I'm loosening it, it's getting lower again. And then when I loosen it back, it's such a crazy difference how just a small change in the tuning peg makes a big difference in the sound. That's all I'm doing right now is changing the tension. But I want to highlight that it only increases with the square root of tension. That's why even a small change makes it. So this is the equation when I make the string half as long. So when I press down on the 12th fret, all of this equations, so this right here is having the string length doubles the frequency, which is 1 octave higher. That's exactly why the note at the 12th fret sounds 1 octave higher than the open string. All right, now I'm gonna explain why, sorry, my phone. The 12th fret on the guitar halves the string. So on a guitar, the frets are placed so that each fret raises the pitch by 1 semitone, which is 1/12 of an octave. There are 12 semitones in 1 octave. So by the time you reach the 12th fret, which is right here, you've gone up exactly 1 octave. So in physics terms, the open string vibrates along its full length, which is L. When you press the string down on the 12th fret, you shorten the vibration portion of the string to half of the original length, which is L divided by 2. The part of the string between the 12th fret and the bridge is now the vibrating segment. The rest between the fret and the nut doesn't vibrate because it's pressed down. And that's why pressing on the 12th fret halves the string.